So today we'll talk about how to draw some polyatomic ions. And like I said, we're going to use those rules to kind of help us with this because, of course, these ones, drawing polyatomic ions, we're going to have a charge. So that means something to us, right? And I think we talked about that yesterday a little bit, you know, when we talked about H3O+, which we're going to talk a lot about H3O+, because H3O+ is a specific ion called the hydronium ion. So this is unit 3 for us. Hydronium is actually what acids are, all right? And so we're going to adjust that a little bit here. So let's take a look at H3O+, hydronium ion. Okay. Now, like I said, for these ones, we are going to use the rules. We're going to add up electrons or take away electrons or whatever the case might be. H3O1+, what does the 1 plus imply? We've what? Gained or lost electrons? We've lost an electron, yes? Think about sodium 1+. It loses 1 electron, yes? Okay, same thing here. So this group of atoms has come together and given off 1 electron, and I'm going to show you why it has to give off 1 electron. So if we're doing this, I'm going to say, okay, well, hydrogen, there is, oops, 1 valence electron for each of the hydrogens, yes? So that's 1, 1, and 1, because I have 3 of them, yes? Okay, so 1 valence electron for each one of those. How many valence electrons does oxygen have? 6, so let's put that on there. And if we add those up, that equals 9, yes? And now what they're saying is this right here means that, hey, we've given off 1 electron, so we've gotten rid of an electron. That's the confusing part, right? But if you think about sodium, for example, sodium 1+, sodium 1+ implies that we've gotten rid of we got rid of 1 electron, so we have 1 less. Well, that's exactly what we have here, so that gives us 8. And that's how many we have to use, just like we kind of did yesterday with that, okay? But that's where the charges come in. We have to adjust for the number of electrons there. So which one would you put in the middle, H's or O's? Or H's or O? Which one goes in the middle? O. O. We're going to draw a skeleton structure. H, 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 okay? Same as we did, this exactly like we did yesterday. The only difference is we added or subtracted electrons at the beginning. That's it. Okay, otherwise it's exactly the same. But the rules here, again, we're going to get a little practice with moving stuff around here. So again, we have to draw a skeleton structure. We have to connect the outside atom to the inside atom. So 1, 2, 3, 4, 5, 6. Okay, so we have to do that. Then remember, okay, and the temptation here is just to keep going, but we really can't. We have to stop there. We've connected the outside atoms to the inside atom. Now we have to make sure that the outside atom is happy. Okay, so we kind of stop. Is this got 2, 2, 2? Okay, then we can move on to the central atom. Yes, and I have 6 used so far. Here comes 7, 8. Okay, is the middle atom happy? Is oxygen good? Got 8? Yep, so we're good. We're going to put brackets around here, though, and a 1+ charge, because if we just drew H3O, I'll show you that, okay? But don't forget to do this, because remember, what did we do when we drew, remember this was about 3 days ago or 4 days ago, what did we do when we drew ionic compounds? We showed arrows, yes? So we show the electron moving over to the non-metal, and then how did we represent it at the end? We drew brackets and charges, yes? Because yes, this is a molecular compound that's come together, they're sharing electrons, but it's acting like an ionic compound that's given off an electron, yes? Or like these atoms have come together, but they're acting like an ion. In other words, they have to get rid of an electron. So it becomes kind of ionic, yes? Okay. If I didn't have the 1+ there, I would have 9 electrons, yes? Well, you tell me, where are you going to put that extra electron to make sure that you have an octet, right? So do you understand why H3O has to get rid of 1 electron? Because where am I going to put it? Like here? Well, then H has too many, right? So we can't do that. And that's why these groups of atoms have come together, and in some cases have to take in more electrons, or in this case has to get rid of 1 because it's got 1 too many, okay? So that's how we get these ions, basically, okay? These polyatomic ions. Good? Questions? Okay, and yep. Yes, you can. So normally I'm gonna, yes, absolutely can. That's a good question, actually. Absolutely you can. I will tell you though, most of the time when you see polyatomic ones, you will probably see this. Okay, but you could, absolutely you can. Okay, so she's asking, can you put the line in here instead of the two dots and line. This, of course, those are the lone pairs, so you'd leave those alone. But you could put lines in there, yeah, absolutely. Most of the time, especially in textbooks and things like that, you'd probably see the dots. It's just kind of how they do it. That's kind of thing. Okay, but you could see lines, yeah, for sure. What's next here? Let's see. What's SO4 2 minus? Perfect. SO4 2 minus. And of course, we'd be talking about sulfate here, yes? Sulfate. So how does sulfate become SO4 2 minus? Hey, how's it going? Good. Right in time. We're just doing sulfate. Yeah. So how does sulfate, SO4, become 2 minus, of course? How does it gain 2 electrons? Well, let's take a look. Again, you have to be very proficient at Lewis diagrams and know how many electrons, how many electrons are in that valence level, right? How many are in sulfur? 6. How many are in each oxygen? 6. Okay. So I'll just do 6, 6, 6, and 6. And how do I do that? That's that part there, okay? And of course, you don't have to write out all those 6s, right? But you do have to add them up, yes? And the 2 minus, remember, implies what? Gained or lost? Gained 2. So I have to add those in as well, okay? So if you add up that should be 32, yeah? 6 times 5, right? And then the 2 extra ones, sorry, 30 and 32, 32. So in this case, like I said, we're going to have a lot of electrons to deal with here, 32 electrons altogether. Good? Okay. So which one are you going to put in the middle? Which one has the best bonding capacity, S or O? Same, okay? So normally, so you might say, well, which one do you, probably most of you would probably pick S, yes? Because it's going to be only one of those. And that's fine. Honestly, it doesn't really matter in the big scheme of things, to be honest. So if we're doing like some other compounds as well, sometimes we pick the one that's by itself and we put that one in the middle, because honestly, it probably doesn't really matter which one's in the middle, because you're going to get the same shapes, all right? So just kind of keep that in mind. This is where it might change a little bit here. You might say, well, I don't know if I want to put the S in the middle, maybe that's fine, okay? It's not the end of the world. You're going to get this shape no matter what, which one you put in the middle. So we're going to start with S in the middle, O's around the outside, skeleton structure, connect the outside to the inside. 1, 2, 3, 4, 5, 6, 7, 8. Okay, and yes, the middle one happens to have an octet. I don't care. Okay, we're not worrying about that now. We got to worry about the outside guys first. So there's 8. I'm going to start here: 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Okay, and now I've used up all the electrons, and the outside atoms are stable. Yes. Okay, or they have their octet, I should say, is what I'm trying to say. The middle one also does as well. I double check that. We're good. We're done. We put brackets here. Boom and boom. Okay, and don't forget the 2 minus though, because if you don't put that there, then you're going to have 32 electrons, and my question is going to be, well, where'd the extra 2 come from, right? Because if we didn't have those 2, we'd be short 2 somewhere, yeah? Like I wouldn't be able to put the last. I wouldn't be able to do 1, 2, 3, 4, 5. I'd be short these 2, for example. So just kind of keep that in mind. Okay, good. Again, sometimes they work out pretty nice and pretty straightforward. Other times they don't. So what else do we got here? I should have another couple examples somewhere. Let's see. NO3. Let's look at that one. So this is nitrate. Okay, NO3 1 minus. Again, we have to kind of go through and decide how many valence electrons we have. Right? So 5, 6, and 6, and 6, and the 1 minus is a 1. Okay, don't get confused with the Don't mess them up there, kind of thing. So 3 O's, so 3 6s, and then that. So that gives me what? 24, yeah? $24. And again, we're going to start with the one with the best bonding capacity usually, but that's not always the case here because we kind of want to keep it symmetrical. It doesn't really matter in these cases, but I'd probably start with an N there, and then an O, and I'll put the other O down there, I guess. I only need 3 of them apparently, okay? So I have 24 electrons to use. Again, we got to connect always outside to inside. These are always the steps: 1, 2, 3, 4, 5, 6. That's where we got to start there, okay? Now, we got to make sure the outside ones are happy first. So that's 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, okay? And I've now used up all my electrons, and the outside ones are happy, and that's key there, right? If the outside ones weren't happy, I'd say perhaps we miscalculated somewhere, because they usually are, okay? So we usually are okay up to this point here. Is the middle atom happy? Okay, so we need to do something about that. And in order to do something about that, and by the way, you can still do this, of course, because that's still true, okay? That is nitrate. It's just not a good drawing of nitrate because nitrogen in the middle does not have its octet. So what do we do with that? Well, same thing we did yesterday, right? What do we got to do? Move a pair in, right? Like we gotta make sure that we're sharing them. So I'm gonna pick which one? This one? Sure. And I'm gonna move that pair into there, for example. And you might say, well, why that one? I don't know. Anyone, pick any pair and move them in, just like we kind of did this yesterday, right? So move those in. And then what I end up with is this. I'm gonna draw this a couple times here. I'll get out of your way right away here. Oops, let me move that over a bit. Okay, and I'm gonna move that pair in to there like so, okay? And remember, when I do that, that pair still belongs to the O, so the O is still good, but now the nitrogen also has its 8 right here, yes? So nitrogen has 8, yes? So we're okay there, okay? And again, which pair do you want to move in? It could be any of those pairs. In fact, probably is all those pairs at some particular time because we really don't know, okay? So I'd pick that there. And again, what you want to do probably, okay, is at this point I'd say, okay, that's fine. There's nothing wrong with that drawing. But of course, in this case here, I'm going to actually jump on Macy's question here and say, well, if you wanted to use the lines or whatever, that's fine. We kind of, eventually down the road here, we kind of want to spread some stuff out, right? Everything's kind of on the bottom, and you'll notice that there's really nothing up here, yes? So there's no lone pairs there taking up a position, so we probably want to kind of spread it out a bit. So maybe, usually what we do is kind of just, this is not a rule or anything, but usually we put the double bond on the top. So that's that right side there. And then we put these two coming out here. Okay, and we'd end up with something like that there perhaps. And again, you can't forget this part, okay? Because if we don't do that, then we don't have that extra electron that we need to make it stable, right? That electron obviously came from probably a metal of some sort, right? We just don't know which one, that's all. Okay, good. Questions on that one, anyone? Yes, no? Don't be shy. And again, you don't have to use the lines. You can use dots there as well. It's all good. Okay, and I think I got one more for you, maybe, I think. Let's see here. Oh, there's the homework. Maybe I don't. Unless there's one. Oh, yeah, I do. Carbonate. Yeah, maybe just real quick. Why don't you guys go ahead and do carbonate here, and then we'll just double check it and make sure we're on the right track here. We'll talk about one more thing, and then, like I said, I'll give you 4 questions here to do. ish, roughly. Again, we want to count up some valence electrons here. So we have what, 4? Each oxygen has 6 valence electrons, so that's what, if you want to just do 18, that's fine. If you can do that in your head, or else get a calculator. And then 2 more, and this means we've gained 2, yeah? So that's what, 24 again? And maybe it'll turn out to be exactly the same as the last one. We really don't know, okay? So in this case here, we're going to put probably C in the middle, I would say, because there's only one of them, first of all. And secondly, C does make a really good central atom, of course. Draw a skeleton structure, put some dots in here. So there's 6 so far. Connect the outside atoms to the inside. Make sure the outside guys are happy first. So that's 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And it looks like, hey, we got the exact same issue as last time, yes? And you're going to kind of find that, for the most part, yeah, there's, we're going to run into kind of similar issues. They're not, I'm going to move this one because I want to change it up today. I'm feeling a little rebellious and a little bit of, like, I want my own expression kind of thing. I'm going to do that with pizza today. And I'm going to put the double bond there. So I'm going to get something like this here probably. And again, what would I have? Boom, 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 boom. And then, that's okay kind of thing. That's nothing wrong with that, especially for right what we know now. And then down the road, eventually, we kind of want to spread that stuff out. So anything around the central atom, we kind of want to spread out into positions as far apart as possible, so that the repulsion, basically, we say, is maximized. And again, we can't forget the 2 minus, please. I would say that's probably one of the biggest mistakes on the quiz, when we have the quiz on this, is that we forget the charges that go with them. And of course, we take some marks off for that just because, again, this is gain 2, so we have to show that. If it didn't have 2, well, we'd have probably maybe a single bond instead, okay? And then that would lead to some other issues maybe, perhaps, okay? Good, questions, anyone? Okay. Like I said, I got 4 questions for you. You guys can work on those. Oh, before you do them though, listen, I'm just going to make one up here. Just well, let's say we just have 2 atoms, A and B. And I'll give you some kind of formula with that. But let's say just two, and I don't know, we'll throw maybe a 1 minus charge, AB. I don't know what it is. But so listen, if you only have 2 atoms, which one's the central one? It's not a trick. Well, it's a trick question. Yeah, I mean, you can still pretend that there is technically there's not going to be a central atom, right? Because I don't know if you know how central atoms work, but if you're in the middle, you got to have somebody over here, and at least over here, to be in the middle, yes? So if there's only me in the chair, who's going to be the middle atom? Well, nobody, kind of thing. But you can still pretend that one guy's the central atom, and that still might help you. So if I have a better bonding capacity than a chair, okay, because we're making relationships here. Come on, hey? I'm trying. That's funny. Huh? Yeah. If I have a better bonding capacity, I hope I do, than the chair, because that would be, ouch, okay? Inanimate object. Then, okay, I should be the central atom, and we should still pretend I'm the central atom. So in other words, we'd put a bond between us, because we got to connect somehow, even with its chair. We're going to put a bond here, but then what am I going to go first? Probably chair. Make sure he's happy first, yes? Make sure he gets the octet, and then I take anything that's left over, yes? Because I'm the central atom. And then, now we might have to move some electrons around, because maybe I don't have enough. So I'm not happy, so chair is going to have to give me some electrons. And let's say chair gives me some electrons. This didn't really work out very well, because I threw it all the way over here. But let's say chair wants to give me some electrons. How many electrons can I take from chair, for example? So let's say you do this kind of thing, and I don't know. Let's say you got that kind of thing. How many pairs can you move in between me and chair, I guess is the question. You can move one pair, yes. We've done that already here, yeah? Right here. This is what I'm saying to you. We can take a pair and move it in, yes? Could you take another pair and move it in? Yes. Okay. Could I take another pair and move it in if I had to? Yeah, you could. Okay. You got to do whatever you got to do to make sure that I'm happy and chair happy, right? And so that we can bond together like this. Oh. This is weird because I don't think the atom sits on the other atom, so I don't know. That doesn't make sense. But you know what I'm saying. Okay, you got to make sure that both of us are happy. So in order to do that, you take as many pairs as you need to make each other happy. Okay, all right. So you might move more than one. That was a good example I had right there. Oh, hey, I just thought of that. Look at me. Hey, 2 years of teaching and I'm doing good. Know-how. And I'm making funny jokes about bonding too. Yeah. Yeah. All right, questions? All right, I'm going to let you guys do some work here. I just got to find them now. Again, these will be in Google. Oopsies, I'm going the wrong way. These will be in Google Classroom, as always. Here's your homework. There's only 4, and then we'll probably move on with some notes here. Bro? No. That's clo. That's chlorine and oxygen, yes. And that's so. Oh, so. And sulfite by the bike racks after school. No, faith, hope, and love. We don't do that here. Okay. Bro, no. Well, you know what I'm saying. Anyway, there's those there. Like I said, they're in Google Classroom as well, so you can check them out there as well if you need to. Okay, or take a picture. It'll last longer. If you want a picture with me, it's fine. Okay, sure.